Okay, welcome everyone. Today, let's start with an important question: is what's robot? Okay, according to the definition in this course, virtually anything that can operate with some degrees of autonomy, we call these robots. So here, the term robot means a computer-controlled industrial manipulator. So as I mentioned in last class, please notice that this course will teach you how to analyze, design, control design, manipulator, but not mobile robot. So if you want to learn more about mobile robot, please select other courses, okay? So in this course, we focused on industrial manipulators. What's the applications of robot? There are many applications of robot in research industrial field, including material transfer. For instance, injection molding or stamping materials transfer. Here, the robot attempts a process to load, unload, and either transfer or stack some finished part or mechanical part here. So we usually use robot to transfer some materials. And execution of a sequence movement. For instance, if this robot can pick up an object from location, home location, and then move to location A, close gripper, and then move to location B, and so on. So here the robot attempts a process to pick and place some mechanical parts here during assembly process. So I think this is an important applications in industrial, because for automation, we usually use robot to pick and place some mechanical parts in factories. And next, welding, grinding, deburring, and so on. Especially grinding and deburring in the mechanical industry. Here, we usually use robot to grinding some mechanical parts and deburring when this mechanical part after precision machining. So we usually use robot here. But in these applications, I think you have to learn more about force control, because you have to control the grinding force or deburring force during the motions of robots. Some other applications, such as processes or artificial limbs. In this research field, you will feel robot will becomes important here, because in some cases, for some human or disabled person, they usually need some, for instance, handicaps or processes to help them walking. So in this field, it is not industrial field, but also important for robot applications. Okay, so we can use robot, especially manipulator, robot arm, in many applications. The applications of robot, as you can see here, are by no means limited to those industrial jobs. As I mentioned, you can use robot to design processes, artificial limbs, to help some disabled or elderly person. There are many other applications of robots in the area where the use of humans is impractical or undesirable. Actually, some hazard conditions, environments, human is usually impractical or undesirable to devote to. So here in this situation, we will use robot, okay, so that we can do some dangerous tasks in some conditions using robot, but not human. Therefore, some methods of analysis and design are required to implement the robotic systems. Okay, about this page, are there any questions? Any questions about this part? No? Great. Next, we move to mathematical modeling of robots. Okay, here I want to introduce some basic notations and terminologies that were used in later chapters. Okay. And the first, also the most important, is the definition of links and joints. So as you can see here, robot manipulators are composed of links. So please notice the word links. Connected by joints. Okay, here, the second important word, joints, to perform kinematic chain. Okay, so for a robot, this robot is usually composed of links and connected by joints. Okay. Moreover, here you can see a revolute joint, actually rotary joint, denoted by R. And the revolute joint is like a hinge that allows relative rotation between two links. Okay, so the revolute joint is a hinge joint. So you can use this joint to connect two links, performs relative rotation motions. Okay. So you can see this figure, and this part plots the this part shows the plot, the draw of a revolute joint. So if you want to draw or you want to design manipulator using manipulator with revolute joint, so you have to draw revolute joint like this in 2D and this in 3D plot. So it is very mathematics. And I suggest you to follow the definition or usual way in robotic research field. So this is important. You have to know the location. Okay. Also, a prismatic joint, also we call the linear joint, okay, denoted by P. So please notice here, use R, capital R, to denote a revolute joint. Please do not use other alphabet to denote the revolute joint. Okay, please. So here you have to use a capital P to denote the prismatic joint. Okay, also please do not use other alphabets to denote the prismatic joint. Okay, so here a prismatic joint allows a linear relative motion between two legs. Okay, linear motion between two legs. Okay, so you can refer to this figure. Also, you can see for 2D plot, you have to use this plot to denote prismatic joint. Also, you have to use this plot to denote the prismatic joint in 3D dimension, in 3 dimensions. Okay. About this, any questions? No? Okay, so here we learned we have to define a revolute joint by R and the prismatic joint by P. Okay, it is very important. Okay, as I mentioned, please use the please use the usual way to denote, to represent some symbols or parts of a robot arm. Okay. Here, each joint allows a single degree of freedom of motion between adjacent links of the manipulator. So here, each joint has only 1 degree of freedom. Okay, in this course, we do not discuss joint with many degrees of freedom. No. For instance, universal joint or other joints, we do not discuss the case here. Okay. Okay, in this course, each joint only has 1 degree of freedom. Moreover, manipulators are usually classified kinematically on the basis of the first 3 joints of the robot arm. Okay, there are many kinds of classification in robotic field. Here is the one classification method to classify the robot arm. We will use the first 3 joints of the robot arm to classify this robot. For example, a 3-link robot arm with 3 revolute joints is an RRR robot arm. Okay, why? Because the first 3 joints are revolute joints. Okay, maybe we will see some examples later. Okay, but here you just need to remember, for one of classification method, we would we usually use the first 3 joints to classify the robot. About this, any questions about this? The classification of robot arm? Oh, okay, great. Here is another important definition of motion, actual motions. Okay, here, the axis of rotation of a revolute joint, or the axis along which a prismatic joint translates, are denoted by ZI. Okay, if the joint connects link I and link I plus 1. Okay, here are 2 examples. Okay, so you can see from this figure, you can see the revolute joint connect link I and link I plus 1. Okay, so we will define the motion of this joint. The motion direction, actually. The motion direction of this joint is here. And this joint, also revolute joint, connect link I plus 1 and link I plus 2. The motion direction of this joint is denoted by ZI plus 1. So we usually define the motion direction of joint by Z, okay? Z direction, okay? So please use other definitions here, okay? Also, you can refer to this figure, and you can see this link is best link. Okay, we usually define this link to be link 0. Okay, link 0 and the link 1 and the link 2. Okay, so you can see there is a revolute joint connect link 0 and the link 1 here. Okay, and then the motion direction of the motion axis. Okay, motion axis of this joint is denoted by Z0. Also, you can see here, there is a prismatic joint here, right? And this joint connect link 1 and link 2. So the motion direction, the motion axis is defined by Z1. Okay. So actually for this figure, you can see this joint, actually joint 1. The direction of joint 1 is maybe inward or outward the plane, okay? The paper plane, okay? And the direction of this joint is along this direction, okay? The direction of this joint is this direction here, okay? So you have to notice that the direction of each joint, because because in kinematic analysis, we have to define the axis motion, joint motion, joint axis first, and then define other coordinates. So it is important to know the motion direction of each joint. Okay, now you can write the note here and here. And if you have any questions, please raise your hand, okay? Here, I think in your lecture note, you can see these figures, okay? So that's why you have to print or bring your lecture note here, because you have to write some note on your lecture note, okay? Also, I will give you time to write the note. Any questions about this part? Okay, please notice the definition of motion axis for each joint. Okay, this figure shows an RRR robot. Why we call this robot arm an RRR robot arm? Because as you can see, the base link 0, is fixed, right? So you can see there is a joint here, and a joint here, and a joint here. These joints are revolute joints, so we call the first three links. The first three joints. So we call this robot arm is RRR robot arm. Okay. And for each joint, we have to define joint variable. Especially here, the joint variable denoted by theta for revolute joint and D for prismatic joint. So also please use theta to define the joint variable of a revolute joint. And please use D to define the joint variable of a prismatic joint. Please do not use other alphabet, okay? As I mentioned, the revolute joint, the joint represent the relative displacement between adjacent links. And this figure shows the representation of an RRR robot. Okay. So you can see here for this joint, actually joint 1, the joint variable is theta 1. And for this joint, the joint variable is theta 2. Also, for this joint, the joint variable. Also, you can see the joint direction, motion direction here. For this joint, the motion direction, because this is a revolute joint, so the motion direction is Z0, okay? Also for this joint, the motion direction is Z1, and for this joint, the motion direction is. Okay, about this part, any questions? Any questions? Great. Okay, then we have to introduce an important concept about configuration, a configuration of a robot arm, okay? According to the definition of, actually original definition of the configuration of a manipulator, you can see a configuration of a manipulator denotes the complete specification of the location of every point on the manipulator. So please notice that here the location includes position and the orientation. Okay, so the configuration actually denotes the complete specification of every point on the robot arm. Also, the set of all configurations is defined as the configuration space. Okay, the set of all configurations is defined as the configuration space. This is the definition, original definition of configuration. Also, we know that, okay, maybe we can refer to this figure. As I mentioned before, here we have we have three revolute joint, and we have three revolute joint variables, right? Here, theta 1, theta 2, and theta 3. So basically, if we know the value of each joint variable, then we can compute or obtain or calculate or get location of every point on this manipulator, right? Actually, I mean, we can calculate the position and orientation of every point on this robot arm. Okay? In the case, we know the values of joint variables. It means if I know theta 1, theta 2, and theta 3, then I can calculate the position and orientation of every point on this robot arm. Okay? So we usually use joint variables to define the configuration of a robot arm. Okay? So you can see the next. As I mentioned, since the industrial links of a robot arm are assumed to be rigid, so we do not discuss the flexible robot arm here. And the base of the robot arm is assumed to be fixed, so we do not discuss mobile robot here. It is straightforward to infer the position, actually position and orientation of any point on the robot arm, okay? If we know the values of joint variables, okay? Of course, these joint variables include angle theta, joint angle theta, and joint offset D for revolute joint and prismatic joint respectively. Okay, about this part, any questions? So in later chapters, you will see we usually use configuration to define the posture or position and the orientation of each point on the manipulated arm. We usually use joint variable to define the calculation. Okay. About this, any questions? About this, any questions? Okay, here is an example. So we can represent a configuration by a set of values for the joint variables. Okay, as I mentioned, because if we know the values of joint variables, then we can infer the position and orientation of each point on this robot. Okay, so usually we denote a vector Q formed by the values of joint variables, and say that the robot is in configuration Q when the joint variables are values Q1, Q2, and the Qn, and so on. So as I mentioned before, here Q denotes the joint variables, okay? And Q equals theta for revolute joint. And the Q equals D for prismatic joint, okay? So please notice that we usually use joint variable Q here, joint variable Q, a vector to denote the configuration, and the vector Q composed by joint variables here, okay? An example, okay, an example, this figure shows actually, I want to ask you, do you know what kind of this robot is? Do you know how to classify this robot? What is? Sorry, I mean, how to, actually, my question is, can you classify this robot arm? Yeah, that's right. Very great. This robot arm is an RRP robot arm. Why? Because the first joints are revolute, and prismatic. Okay, so we call this robot arm is an RRP robot arm. Okay. Also, we can define joint variables here. Theta 1 for revolute joint 1, and theta 2 for revolute joint 2, and D3. Remember the variables. The variable here for prismatic joint, D3 for the third joint, prismatic joint. So we called this robot is an RRP robot arm. Okay? About this, any questions? And then for this robot arm, we will define its configuration Q. So you can see here the configuration Q is formed by joint variables here, Q1, Q2, and Q3. So we usually use Q to denote the joint variable, okay? So we can define the configuration of this robot arm by this vector Q, okay? And the Q is formed by joint variables Q1, Q2, and Q3. Actually, we know that Q1 equals theta 1, Q2 equals theta 2, and Q3 equals D3. Okay, here, why? Because joint 1 and joint 2 are revolute joint. Okay, so the joint variables, actual joint variables are theta 1 and theta 2. And the third joint is prismatic. So we define the joint variable Q3 to be D3. Okay. So about this part, any questions? So in this lecture, introduction lecture, we will let you know some notations, terminologies, definitions will be used in later chapters. So I hope you can remember, okay, keep in your mind these notations, symbols, definitions, okay, to help you study in later chapter. Any questions? No? Great. Next, we move to the definition of degrees of freedom. Okay, here we know that an object is said to have n degrees of freedom if its configuration can be minimally specified by n parameters. Okay, it's the definition of DOF, degrees of freedom. Okay, we uh, we we said that. Okay, an object. The definition is an object has an object has n DOF if its configuration can be minimally specified by n parameters. Okay, so in this case, what is the DOF of this robot arm? Do you know that? What is the DOF of this robot arm for this case? Okay, I think A, the DOF is 3, right? 3, right? Okay, good. But please notice that so here is an example of a rigid object in three-dimensional space. Okay, a rigid object in three-dimensional space has 6 degrees of freedom. Why? Because 3 for position and 3 for orientation. Okay, so we know that before. Actually, we knew that before. Okay, why? Because the configuration of this object can be specified by 6 parameters. As I mentioned, 3 for position and 3 for orientation. Okay. But please notice that for robot arm, for manipulators, the number of DOF is equal to the dimension of the configuration space. Okay. So the original definition of DOF of a robot arm is the number of DOF is equal to the dimension of the configuration space. Okay, what is the configuration space? The dimension before the configuration space is defined as the set of all configurations. Actually, composed of all the sorry. And here, as I mentioned, the number of DOF is equal to the dimension of the configuration space. Okay, about this, any questions? Okay, so do you know what is the dimension of a configuration space? So do you know what is the dimension of the configuration space? Actually, do you know what is the definition of a vector space? You know that? Okay, as I mentioned, before you decide to take this course, you have to learn some linear algebra. Okay, so here I think you have to know what is the definition of vector space. Okay, so then you will know, you will understand why we define the dimension, why we define the DOF is equal to the dimension of the configuration space. Okay, and this part belongs to linear algebra, fundamental of linear algebra. Okay. So here, please notice that the number of DOF is equal to the dimension of the configuration space. And the number of joints determines the number of DOF. About this part, any questions? Okay. Maybe I can give you an example. Okay. For instance, a robot arm has maybe 5 joints, okay? A robot arm has 5 joints. So we can define the configuration of this robot arm by this vector. Okay, Q1, Q2, Q5. Okay, so we use this vector to define the configuration of this robot arm. This robot arm has 5 joints. Okay, so what is the definition of the configuration space? So this is a vector, right? This is a vector, right? So from this vector, we, according to the definition of vector space, we can define the dimension of this vector space. Actually, the dimension of the configuration space, okay? Dimension of the configuration space. We can define the dimension of the configuration space. Okay, so I think, do you think the dimension of this vector space, actually this configuration space, would be 5? Oh, no, that's right. Actually, the dimension of a vector space is not equals to the number of joints. Understand? So you cannot use the number of joints to define the dimension of configuration space. Also define the configuration of this robot arm, the degrees of freedom of this robot arm. Okay? It is very important. Why? Because we will learn a word we call redundant robot. Okay? So here, we know that the number of joints determines the number of DOF. But the number, here, see, the number of joints is not equal to the number of DOF. It is very important. Okay, about this part, any questions? So as I mentioned before, if you want to know more detail about the definition of a vector space, I think you have to learn linear algebra before, right? Okay. You have learned the linear algebra. So here, according to the definition of DOF, the configuration of an object can be minimally specified by n parameters. Okay, this is the definition here. And here. This is the definition of DOF. Okay, the configuration of an object can be minimally, please notice that, minimally specified by n parameters of the configuration space is Rm. Okay, we usually use this symbol to denote to represent a vector space. Okay, Rm denotes that the vector space has m dimension. Okay, the vector space has m dimension, and in this space, each element are real. Each element is real. Okay. Okay, so this sentence, the configuration of an object, okay, minimally specified of the part is completely defined by m. Okay, so n and m different. Okay, so here we can get n equals n, m equals n. Okay, if the configuration can be minimally specified by n, and the configuration completely specified by m, then we say m equals n in this case. Okay. However, here please notice that m is not equals to number of joints. As I mentioned before, the number of joints here, see, the number of joints determines the number of DOF, but the number of joints is not equal to number of DOF. So here, please notice that the configuration space, actually the dimension of the configuration space is not equal to number of joints. So this is very important. Okay. Here is an example. You can see that. we can construct a small configuration space by a manipulator with many joints. Okay. So here we can construct a robot arm, okay, with many joints, but its dimension actually its dimension of configuration space is fewer than the number of joints in this case. Okay. Okay, here we take a break, 10 minutes. Okay. And then I will introduce the example. Okay. Okay, here is an example. We can construct a small configuration space, actually a robot with small configuration space. But this robot may have many joints. Okay, here I can give you an example. For instance, for this robot arm, fix the best, okay? So this is a planar robot, okay? Planar robot. And they are 1, 2, 3, 4, 5, 6, 7, 8. They are 8 joints. 8 joint planar robot. Okay, this robot is a planar robot. Okay, a planar robot, but this robot has 8 joint, revolute joint. Okay, revolute joint. Revolute joint. Okay, I want to ask you a question. What is the dimension of DOF of this robot arm? What is the dimension? What is the DOF, number of DOF, actually? 2, really? Why? Planar robot. 1? Why? This is a planar robot, please. Why? Actually, 3. Why? X, Y, and theta, right? We can use 3 variables to three, only 3. Okay? But this robot arm has 8 joints, right? So as I mentioned before, the number of DOF is not equal to number of joints. Okay? Sorry. This robot arm, the degrees of freedom of this robot arm is 3. Okay? But the number of joints of this robot arm is 8. So this case is the case I mentioned. The number of joints is not equal to the number of joints. Okay? Why do we design this robot? Why? Why do we design this robot? Why we design this robot, actually? Okay? Because, oh, sorry. For instance, if I want this robot to capture an object behind an obstacle. Okay, for instance, there is an obstacle here. There is an obstacle here, and there is an object here. Okay, there is an object here. I want to use this robot arm to get this object. But there is an obstacle here. How? How to control this robot arm to get this object? There is an obstacle here. So we usually design a robot with redundant joint to capture an object behind an obstacle. Okay, by this posture. Okay. So in this case, we will design a robot with redundant joint. For the reason why we have to design a robot arm with more joints. Okay, even this robot arm is a planar robot arm. Any questions about this? So I mentioned, and maybe not important, I mentioned a keyword, redundant. Yeah, right? Redundant. So as I mentioned, in some cases, the number of joints is not equal to the number of DOF. In this case, this robot is redundant. Okay. In this case, this robot is redundant robot. Okay. So that's why we usually design a redundant robot to do some tasks, especially complex tasks. Okay. Any questions about this part? Okay. Any questions? So here I give you few time to think about this, okay? Because this concept is very important, especially if you want to design a robot arm to perform some complex tasks. Any questions? No? That's great. Okay. So here you can see a manipulator should typically possess at least 6 independent degrees of freedom to approach any point in a three-dimensional space with arbitrary orientation. So why? Because an object in three-dimensional space has 6 degrees of freedom, right? So if we want to design a robot arm to capture the object in three-dimensional space with any arbitrary position and arbitrary orientation, then we have to design the robot arm. This has 6 degrees of freedom. Okay. If we want to design a robot arm to capture an object in three-dimensional space, then we have a robot arm at least has 6 degrees of freedom. Okay. So here you can see a robot arm with fewer than 6 degrees of freedom cannot reach any point in its workspace with arbitrary orientation. Okay, so I think this is very important for you. If you want to create, you want to build a robot arm to do some tasks in three-dimensional space. Okay. So, for instance, the scalar robot. Okay. We will describe this robot later. The scalar robot has 4 joints. Okay, has 4 joints. So you know the number of degrees of freedom of the scalar robot is fewer than 6, right? Fewer than 6, right? So the scalar robot cannot reach cannot reach every point in its workspace with arbitrary orientation. Okay, so we usually use this robot arm to do some simple tasks. Okay, especially maybe three-dimensional space. Yeah, okay. Because the DOF of this robot is fewer than 6. So we cannot use this robot arm to do some complex tasks in three-dimensional space. Any question about this? This robot is very important, and I will describe and I will introduce this robot arm later, okay? Including kinematics analysis, forward and reverse, and inverse, sorry, forward and inverse kinematic analysis. Any questions about this? Oh, okay, great. However, as I mentioned, as the example I gave you before, for some applications, such as reaching around or behind obstacles, the robot arm may require more than 6 degrees, more than 6 joints, 6 degrees of freedom. Okay, as I mentioned before, because if your robot want to capture an object behind obstacles behind an obstacle, then you have to design a redundant robot to perform the task. Okay. So here, a robot arm manipulator having more than 6 DOF is referred to as redundant robot arm. So usually you will see these words, redundant robot arm or redundant manipulator. Okay. Any questions about this part? Any questions? This part is important because, as I mentioned, in your research field, maybe you have to understand what is the definition of redundant robot, okay? And what's the purpose of using the redundant robot, and how to control the redundant robot, okay? Any questions? So far, we know that a configuration provides an instantaneous description of the geometry of a robot arm, but says nothing about its dynamics. So we usually use configuration, the vector Q. Do you remember that? Motion of the robot arm, but just describe the geometry of this robot arm. Okay, say nothing about its dynamics. Okay, kinematics, but not dynamics. Okay, we use this to represent the kinematics of this robot arm, but not dynamics of this robot arm. Okay. About the definition of state and the state space of the manipulator. Okay. The definition of state and what is the state space. Okay. Here you can see the state of a robot arm is a set of variables that is sufficient to determine the time response of the manipulator. For instance, we can define velocity and the position of this robot arm to be states of this robot arm. Okay. So what is the state of a robot? The state is a variable, okay? And this variable can be used to determine the time response of the robot arm. Also similar to configuration space, what is the definition of state space? Okay, so here we have to think about the concept of vector space again, okay? Similar to configuration space. So here, what is the definition of state space? Okay, here, the state space is defined as the set of all possible states, okay? So we define the state space here. In the case of a manipulator, a state together with a manipulator's dynamics and inputs can be specified by given the values for the joint variable Q and Q dot. So this description, this statement, okay, mentioned we can define state of a robot arm by its joint variables and its joint velocity. Okay, so we can define the state of a robot arm by its joint variable and the joint velocity. Okay, and then if we give the system, okay, sorry, if we give the here, if we give actually, if we know the dynamics of this robot arm and give the inputs, then we can calculate the joint variable Q and the joint velocity here. Okay. Here is an example. Okay, see? The joint acceleration Q double dot is related to the derivative of joint velocity. I think we knew that. We knew this part before. Okay, so here is an example. The dynamics of a manipulator can be written like this. Okay, so we usually represent the dynamics of a manipulator by this equation. Okay, so after chapter 7, we will see this equation many times. And in this case, we can define the state of this robot arm. We can define the state of this robot arm here, or the state x of this robot arm by this equation. X equals a vector composed by Q and Q dot. Okay, so we define the state of this robot arm X here. And then we can rewrite the dynamic equation. We can rewrite the dynamic equation to be this equation, okay? We can rewrite the dynamic equation to this, okay? Here, the function, I have to mention x dot equals function of x and the tau. Here x is the state of this robot arm. Okay, as I mentioned, defined by this vector. Okay, and here f is a nonlinear function. Okay, so unfortunately, we have to deal these nonlinear functions if we want to design a control rule to control this robot arm. Okay, so as I mentioned, this function f is nonlinear function. Also, it is a vector. Okay, a function. Sorry, actually, it is a vector composed of many functions, nonlinear functions. Okay. So this is the definition of state and the definition of Actually, we call this equation is the state equation. Okay. If you have learned some control method such as advanced control or something else, then you have learned this equation, okay, before. Automatic control, advanced automatic control. Okay, about this part, any questions? About this part, the definition of state and the form, actually I have to say the form of dynamic equations. Okay, we have the original dynamic equation like this, and then we can write the dynamic equation like this. So we have to know that the dynamic equation is multivariable and nonlinear. So it is usually difficult for some students, okay, to design the control system to control the robot arm. Any questions about this part? The definition of state and the form of dynamic equation. Any questions? No? Okay. Next, I want to introduce the concept of workspace. Okay, what is the definition of the workspace of a manipulator? Okay, you can see here the definition of the workspace is the total volume swept out by the end effector when the robot arm executes all possible motions. So we define the workspace like this. So here, I think you do not understand yet what is an effector. I will describe this later. An effector. Okay. So here, I think you can think the end effector is similar to the palm of your how to say that, your arm. Okay. Okay. I think you can think the end effector similar to your finger. Okay, your finger on your arm, and then if you swipe your arm, and then the finger will sweat out a workspace, a space. Okay, so we can define this space to be the workspace of your arm. Okay, so we can define the workspace of the robot like this. Okay, so the robot executes all possible motions. And obviously, the workspace is constrained by the geometry of the robot arm and the mechanical constraint of the joint. So you can see that different kinds of robots composed by different geometry, joints, they will have different workspace, okay? So this is the definition of workspace. Are there any questions about this part? Okay, maybe here I can give you some examples about the workspace of different manipulators. You can see here. So here there are 4 robot arms. Okay. This robot arm is RRP robot arm. And this robot arm also RRP robot arm. But depends on the different geometry. So its workspace are quite different. See, the workspace of this robot arm like a shell. Okay. And the workspace of this robot arm like a cylinder, 3-dimensional cylinder. Okay. Yeah. And this is our PP robot arm. And the workspace like cylinder. And this is PPP robot arm. And the workspace is rectangular. Okay. So here you can see this point is the point on any vector. So when this robot arm performs all possible motions, then this point will sweep out a volume. Okay, sweep out a volume. Then this volume is the workspace of this robot arm. Okay. This is the definition of workspace. Yeah. This is the definition of workspace. Yeah. Right. And then there are 2 kinds of workspace for manipulators, including reachable workspace and dexterous workspace. Okay, so there are 2 kinds of workspace for manipulators. What is reachable workspace? So you can see reachable workspace denotes the entire set of points reachable by the manipulator. Okay, so we define this to be reachable workspace. Okay, and what is the dexterous? Dexterous workspace. Dexterous workspace denotes the set of points that the manipulator can reach with arbitrary orientation. So what is the difference between reachable and dexterous workspaces? You can see the dexterous workspace denotes the points can be reached with an arbitrary orientation. Okay? Can be reached with arbitrary orientations. But reachable workspace denotes the points can be reached by manipulator. Okay? So this is the difference between reachable and dexterous workspace. About this part, any questions? Okay, maybe I can give you an example. Okay, for my hand. Okay, this is my hand, and this point, the point on the microphone. Okay, this point, my hand can reach this point, right? This point is the so this point is in the reachable workspace. Okay, but can I this point is the point in space. Okay, but now this point, my hand can reach this point with arbitrary. is in the Dexter's workspace. Okay, so now you know, do you know the definition of these two workspaces? Okay, reachable and dexterous. Okay, so clearly the dexterous workspace is a subset of reachable workspace. Okay. Any questions about this part? A definition of workspace, reachable and dexterous. Any questions? Okay, maybe I can introduce. This robot arm is spherical robot arm, and this robot arm is scalar robot arm, cylindrical robot arm, and Cartesian robot arm. Okay. Any questions about this part? Actually, robots can be one kind of mechanical devices. Okay, we know that. Yeah. Robot can be one kind of mechanical devices. So the classification of robot arm, there are many kinds of classification of to classify. There are many methods. There are many methods to classify the robot arm. For instance, we can use power source, control method, and the application, and so on to classify the robot arm. So first, I want to introduce the classification of robot arm using power source. Okay. There are many power can be used in robot arms. Okay, in industrial applications. For instance, the hydraulic robots. Okay, here the hydraulic robots are usually used to lifting heavy loads. Okay, so you can see, for instance, you can see some excavator. Okay, excavator on the road. Sorry, these words. Excavator,挖土机啊。On the road, a hydraulic robot arm. Okay, and this robot arm have some drawbacks, such as leakage and the requirement of peripheral equipment, such as pumps, pipes, and so on. Also, there are some noise. That will limit the application of this kind of robot arm, hydraulic robot arm. So you can see they are actually in semiconductor industry. They won't use this kind of robot. Okay, hydraulic robot arm. Okay, and the pneumatic robot arm are inexpensive and simple, but cannot be controlled precisely. This statement is quite different. Okay, pneumatic robots are inexpensive. I'm not sure actually. Okay, and simple? No, I don't think so. But they cannot be controlled precisely. Yes, okay, we cannot precisely control the pneumatic robot. Okay. And in most applications, we usually use electric robots. And the electric robots driven by AC or DC motors. And this kind of robot cheaper, cleaner, and quieter than the others. Okay, cheaper, I'm not sure. Okay, maybe you can buy some expensive robot arm composed by electric motors. Okay? But this kind of robot is cleaner. Okay, that's right. And quieter. Oh, okay. So we can use power source to classify robot arm. About this part, any questions about this part? Oh, okay. Also, we can classify robot arm by control method here. Okay, so we can refer to this figure. A control system of a manipulator. Okay, the control system of a robot arm here, composed of robot arm here, power supply here, power, tooling, and effector for tools. Also, we can install some sensors and so on. So you can see this structure is general for many industrial robots. Okay. So we have to use a computer to control this robot arm. And this computer also have to receive some information from sensors. Also, we have to program the motions of this robot arm. So we have to, we need program storage or network. Okay. And in industrial applications, we also need input device. Here we call the teach pattern. Okay, teach pattern. So that we can teach the robot arm to perform. Sorry, we can teach the robot arm to perform some tasks. Okay, here we have to use the teach pattern called 教导盒. Okay, and this device is quite expensive, as I remember. Okay, this block diagram. Okay, this block diagram represents the general control system of a robot arms, and depending on the control method, we can classify robots to be non-servo robots and servo robots. Okay, what is non-servo robots? This kind of robot usually use open loop devices and open loop control, making their movements limited to limited to predetermined mechanical. For instance, you can design a robot arm with a simple structure, and this robot arm can move in your workspace. Okay, in your workspace or in your factory. Okay, and then this robot arm is quite simple. When this robot arm moves and touches a limit switch, then this robot arm is stopped. Okay, so we use this kind of operation to control the motions of this robot arm. So we call this robot arm is non-servo robot arm. Non-servo robot arm. Okay, open loop device and open loop control. Another robot we call the servo robot. Okay, and this robot uses closed loop control to determine and effectors motions. Okay, here the most important, we have to use closed loop control to control the motion of an effector. Okay, in this case, we can divide this robot to be point-to-point robot and continuous path robot. Okay, what is point-to-point robot? It means this robot can move from one position to other positions. And actually, we do not care about the motion of this robot. Okay, we do not care the motions, including path, velocity, and so on, about this robot. But the most important is this robot must reach the point precisely. Okay, here point also denote position and orientation. So we have to know that. What is continuous path robot? It means the entire path of the robot arm must be controlled. Okay, we have to control the motions of this robot. Actually, precisely control the motion of this robot. Okay, so this application we call the continuous path robot. For instance, we can use robot arm to do machining tasks. Okay, a hot topic in recent, we call the machining robot. Okay, in this case, the robot must be continuous path robot. Okay. About this part, any questions? Okay, we can classify robot arm by control method. We also can classify robot arm by application area. Okay, so here application area divided to assembly and non-assembly. Okay, so here assembly and non-assembly robots depends on the level of precision required in assembly tasks. Okay, so here we can see what is assembly robot. Okay, assembly robots are usually applied to perform part insertion operations. Okay, this operation has a famous problem we called packing hole problem. Okay, we use this robot to perform some insertion operations. So we can see that a slight mismatch between the part and the tool can result in wedging or jamming. Okay, and of course, these operations can cause large insertion, interaction forces, and the failure task. So this control is here. Packing hole problem. Okay. Also, you can find some literature, some papers to solve this problem. Okay. Also, you can think if you want to control the robot arm to perform some insertion operations, you have to use, for instance, you have to use some force sensors, okay, in your control system, so that you can control the interaction force and to prevent the failure of the task. Okay. Oh yeah, here you can see that it is difficult to accomplish the task without sensing or controlling the interforce. So here, especially you have to use sensors, right? To sense, to detect the interaction force. Also, you have to use some advanced control technologies. For instance, you have to use force control, hybrid control, impedance control also to control the robot arm to perform some precise assembly task. Okay. About the assembly robot, any questions? Any questions about this part? No? Great. Okay, what is non-assembly robot? Assembly robot is usually applied to welding, spraying, spray painting, material handling, and machine loading and unloading. So these operations are classified to non-assembly robots. Okay. Any questions about this? Assembly and non-assembly. Also, we can classify the robot arm using its geometry. Okay. As I mentioned before, the robot arm are usually classified kinematically according to the basis of the first three joints. Okay, so we saw many cases before, right? R robot, RP, RPP, and PPP robot. Okay, so here an example of R robot arm is articulated robot arm. Also, the RP robot arm, spherical robot arm, scalar robot arm are both RP robot arm. And the cylindrical robot arm, RPP robot arm, partition robot arm is PPP robot arm. So as I mentioned, you can see there are many here. So this robot arm is RP robot arm. This robot arm is here, spherical robot arm. Okay, and this is RP, this is RPP, and this is. So we can use, we can classify robot arm by its geometry. Also, we can classify robot arm by the connection of links. Okay, so you can see serial link robots are composed of links connected by joints to form an open loop kinematic chain. Okay, so we can see there are many serial link robots here. This robot, and this robot are serial link robots. Okay, and parallel robots. Okay, the most important is parallel robots. Okay, parallel robots are composed of links that are arranged in a closed loop kinematic chain. Okay, for instance, you can, if you know Stewart robot arm, also you can see what moment. Okay, this is parallel robot. Okay, you can see all links, the links of this robot arm construct a closed loop kinematic chain here. So here is a loop and here is the loop. Okay, so this robot is parallel. Also, I think you know that Delta robot, right? Delta robot is a parallel robot. And unfortunately, parallel robots kinematics and dynamics are more difficult to derive than those of serial link robots. So in this course, we do not discuss about parallel robots. We focused on our topics on serial link robots. Okay. Are there any questions? Okay, let's take a break. 10 minutes. Okay. Any questions about this course or something else? Any questions? No, really? Very good. Actually, I want to know how many foreign students in this classroom. Are you foreign students? Please raise your hand. Foreign students. Do we have any foreign students here? No, really? No. We cannot speak in Chinese because this course is an English course, especially for English course. Okay, so I have to teach you using English, right? Okay. Any questions about this part? Actually, I'm not sure. Do you have any chance to practice your English? Do you have any chance to practice your English? Do you? Few times. Oh, that's great. Okay. How about other students? Yeah, I think you can think this is this course in this classroom is the opportunity to let you practice your English. Okay, so I encourage you to speak, to discuss using English. Okay, in this classroom. Okay, in this class, in this. I So that's why we have to use English, okay, in this. This is the great chance, opportunity, okay, practice. Okay, any questions about this course or the part of lecture? Any questions? Okay, next, I want to introduce what are risks and end effector. Actually, we see this phrase before, right? End effector. But what is the end effector of a rope arm? Okay, according to the definition, the joint in the kinematic chain between the arm and the end effector are referred to as the wrist. So here we have to know what is the arm, also what is the end effector. Okay, here you can think about this. What is the wrist? The joint between arm and the end effector. Okay. Especially, it is required to design robot arms with spherical wrist. Okay, here. So what is spherical wrist? Okay, spherical wrist has three joint axes, revolute joint, okay? Three joint axes interacting at a common point. Okay, so you can refer to this figure, okay? This joint is a spherical joint. Sorry, this wrist is a spherical wrist, okay? And this wrist has three, see, 1, 2, 3, three joint axis, revolute joint axis, okay? And these axes interact at a common point here. This point is the wrist center point, okay? Wrist center is spherical wrist, okay? What is spherical wrist? And also, what is the wrist center point? Okay, the wrist center point and the spherical wrist. Okay, spherical wrist is quite important in robotics. Okay, why? Because we will analyze the inverse kinematics of a robot arm, and if the robot arm uses a spherical wrist, then we can decouple the complex problem, inverse kinematic problems, into two simple problems, okay? Into two simple problems, okay? So the spherical wrist is very, very, very important, okay? About this, any questions? The definition of wrist, the definition of any vector, also the definition of spherical wrist and the wrist center point. Any questions about this? Any questions? Yeah? Oh, no, 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 we cannot. We cannot. It's quite different. Okay? So actually you can see here, roll, pitch, and yaw are quite different from X and Y and Z. Okay? But you can think it's they are the rotation angle of X and Y and Z axis. Rotation angle. Okay, so yaw, here roll, pitch, and yaw, you can think these angles denote the rotation angles of X, Y, and Z axis. Okay, but they are not X, Y, and Z axis. Okay, okay, very good. Any questions? Other questions? Okay, so I have to mention again, emphasize, okay, emphasize. Again, spherical wrist is very important. Also, you have to know the definition of wrist sample point, okay? Here, as I just mentioned, the axis of rotation, see here, the axis of rotation of the spherical wrist are typically denoted roll, pitch, and yaw. Okay, so axis of rotation, okay, rotation of each axis, okay, we called roll, pitch, and yaw. Okay. Also, it is important that the spherical wrist, or here, as I mentioned before, the spherical wrist can greatly simplify kinematic analysis, especially inverse kinematic analysis, because it allows one to decouple the position and orientation of the end effector. Okay, so as I mentioned before, if in the inverse kinematics, in the inverse kinematic analysis, if your robot arm uses spherical wrist, then we can decouple the inverse kinematic problem into two small problems. Here, position, actually inverse position problem and the inverse orientation problem. In the case, just in the case, the robot arm uses spherical wrist. Okay? So I have to mention again, spherical wrist is very, very, very important in robotics. Okay? Any questions about this part? Any questions? Oh, great. So now you know what the wrist is and what the spherical wrist is. Next, I want to introduce some common kinematic arrangements. Here, as I mentioned before, we can classify manipulators, robot arms using geometry of the first three joints, right? So here are some examples, common examples. Articulated robot arm, spherical robot arm, scalar robot arm, cylindrical robot arm, Cartesian robot arm, and parallel robot arm. Okay, the first example is the articulated manipulator. Also, this robot arm is RRR robot arm. It is RRR robot arm. As you can see from this figure, the first three joints are revolute. So we called this robot arm RRR robot arm. This robot arm is also called a revolute elbow. Anthropomorphic. Oh, okay, this word is difficult for me, right? Manipulator, okay? Articulated, actually, we usually call articulated robot arm, okay? And this figure also shows the workspace of this robot arm here, the workspace of this robot arm. And you can see the design of this robot arm locating as much of the mass of the robot away from the distal link as possible. It means you can think robot arm is similar to a cantilever beam, right? So if you want to control this robot arm to perform some precise tasks, you have to locate the mass of this robot away from the distal link here, away from this link, okay, to prevent bending, okay. Any questions about this robot arm? Articulated robot arm. In later chapters, we will see this robot arm many times, okay? Because this robot arm is important, but simple, okay? The next robot arm is spherical robot arm here. Spherical robot arm, also RRP robot arm. Okay, this figure shows the spherical robot arm. And why we called this robot arm spherical robot arm? Because its joint coordinates coincide with spherical coordinates. Okay, so we called this robot arm spherical robot arm. And also you can see the workspace of this robot arm. As you can see from this figure, the workspace is similar to spherical shell, okay? Spherical shell. And this photo shows the spherical robot arm, I think. Okay. Any questions? Any questions about this robot arm? Yeah, spherical robot arm manipulator. Usually, in industrial application, we usually call the robot arm, but not a manipulator, okay? In industrial application, we used to call robot to be robot arm, but not manipulator. But in academic research field, we usually call the robot, this kind of robot, to be manipulator, but not robot arm. Okay, so you why I how to say that? I usually use robot arm because its pronunciation is quite simple. Okay, but manipulator, the pronunciation is quite difficult for me. So I usually use robot arm, but not manipulator. Okay. Any questions about this robot arm? Spherical robot arm, RRP robot arm. There is another RRP robot arm we call the scalar robot arm here. We call the scalar robot arm. So as you can see from this figure, it is RRP robot arm, right? Scalar means selective, compliant, articulated robot for assembly. So we usually use this robot to do some assembly task. Okay. And you can see what is the difference between this robot and this robot. What is the difference between scalar robot and spherical robot? What is the difference? Yeah, that's right. That's right. You can see for the scalar robot, all axes, right? All axes are parallel. Okay, see? The motion axis of the first joint, the second joint, and the third joint. Okay, but in this robot arm, the motion axis of the first joint, the second joint, and the third joint. So you can see here, although this robot is an RRP robot arm, but all axes are mutually parallel. Okay, so a robot arm, especially a robot arm with 3 parallel motion axes, we call this robot arm to be scalar robot arm. Okay, any questions about the definition of scalar robot? Also, you can see the workspace of this robot arm like this. You can imagine that why we usually use robot to do some assembly task. Okay, quite simple. Yeah, here. The scalar robot is defined as the manipulator that has RRP structure and the mutual parallel joint axis. Okay, RP structure with parallel joint axis. We call this robot scalar robot. Okay. Any questions about this part? Scalar robot is very important. Okay. So I think you have to know is kinematics analysis, including forward and inverse kinematics. And you have to know how to control this robot arm. Okay. Any questions about this part? Okay. Next, I want to introduce cylindrical robot arm. It is RPP robot arm. Okay, as you can see from this figure, all joint variables here, all joint variables are cylindrical coordinates. Okay,
actually coincides with the cylindrical coordinate. Okay. So you can see here the revolutor joint, prismatic joint, and the prismatic joint here. Okay, this robot, this photo shows the cylindrical robot arm. And this figure shows the workspace of the cylindrical robot arm. So as you can see, the workspace is similar to the cylindrical shell, right? So this robot arm, cylindrical robot arm. The next is Cartesian robot arm here. Okay, this figure shows the Cartesian robot arm and all joint variables. Why we call this robot arm Cartesian robot arm? Because all joint variables are, see, Cartesian coordinates. Okay, joint variables are equal to Cartesian coordinates. So we call this robot arm PPP robot arm. Okay. This robot arm is widely used in industrial applications, especially machining, and cutting conditions. Okay, applications. Sorry. Why? Because this robot arm can provide increased structure rigidity. Okay, and therefore this robot arm can provide higher motion precision. Okay, so in industrial application, if you do not consider orientation of the tool, then we usually use this robot arm in industry. Okay. Also, you can see the workspace of this robot arm like a cube. Okay. Any questions about this robot arm? Any questions? No? Great. The next is parallel robot arm. Here, parallel robot arm. Okay, this figure shows a parallel robot arm. Okay, also you can see there are some some subset of links formed across the chain. Okay, so you can see here is a cross chain, and here is a crossed chain. Okay, and for parallel robot, there are two or more kinematic chains. Okay, connecting to the base. Also, you familiar with the robotic research field or industrial applications, you can see Delta robot, right? Delta robot is a parallel robot. Okay. Okay, see here, this robot can provide much higher rigidity than serial link robot. So in some machining or cutting applications, we can see the machine tool use this parallel robot. Okay, so you can install a cutting tool here, and then perform some cutting tasks or machining tasks. Okay. Any questions about this part? This manipulator robot arm? As I mentioned before, a study of this parallel robot arm is quite difficult. Okay, so this course does not focus on this robot arm. This course focused on serial link robot arm. Okay, so you don't need to worry about this. Okay, but I think if you learned some fundamentals about robotics, through this course, then you will get some fundamentals to study this robot arm. Okay? Any questions? Yeah. Okay. You can see, as I mentioned, we can use this robot because this robot has higher rigidity. So we can use this robot in some machining applications or cutting applications. So you can see some machine tools use this robot. Okay. Answer your question? Really? Okay. Any other questions? So as I mentioned, so do you know Delta robots? Do you know Delta robots? Delta robots. Yeah. No. Delta robots. This is Delta robot. Okay. But not, we call this robot Delta robot, but not because the manufacturer, okay? Because it's form, structure, okay? So this is Delta robot, okay? Delta robot. So this robot is parallel robot, okay? We usually use this robot to pick and place, right? Also, maybe I can show you some. See, there are many kinds of parallel robots, okay? And we usually use this robot to do some machining task, okay? So you can see there are some machine tools use this robot arm, okay, parallel robot arm, okay, see? Also, we can hexapod, a special name we call the hexapod robot arm. Actually, I think its operation is quite amazing. See, parallel robot. Show you another. I remember a company famous in this field. Okay. Also, steward. Steward platform is a parallel robot. See? Okay, this is we call the steward robot. Okay. Here you can see this robot in simulation, flight simulation, right? Okay. Any other questions? Okay. Rigidity. Yeah. The dimension before. See? Comparing with the traditional serial link robot, this robot can provide higher rigidity. Okay. And rapid motion. Okay, rigidity and rapid motion. So we usually use delta robot, as you see from the YouTube. We usually use the delta robot to do some pick and place tasks required rapid motion. Okay. Any other questions? Any other questions? No? Okay. So in the next, I want to use an example to let you know what topics will be introduced in this course. It means if you want to control a manipulator, robot arm, you have to consider what topics. Okay, for instance, you have to know how to control, how to move the manipulator from a point to another point. Okay, using a desired velocity. So here we have to learn some topics, including forward kinematics, inverse kinematics, velocity kinematics. Also, we have to learn path planning and trajectory generation. Okay. The most important, if you want to control this robot moves precisely, rapidly, then you have to do some study on control technologies, including independent joint control, dynamics, multivariable control, and force control. Okay. So in the next, I want to use this example to let you know what topics I will introduce in this course. And this example, this figure shows a manipulator with a grinding tool. So here, a tool with a tool here, so that this manipulator can be used to remove certain amount of materials from the surface. Okay, so this is an grinding robot example. This is a grinding robot example. Okay, and because this is a new topic, so I want to introduce this example in next. Okay, about today's class, any questions? No? Okay, Okay, I remember one thing. I want to have a local. Just a moment, okay. Up. Just a moment.